Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the second derivative test. So what this test is used for is classifying stationary points as either a maximum, minimum, or an inflection point. So let's look at this diagram here. This is just a graph of a random function fx. So it has a maximum at point A, it has a minimum at point B, and point C, you may or may not have seen, is an inflection point. It's where the graph becomes flat for just an instant, so it's a stationary point, but the graph doesn't change from being increasing to decreasing or vice versa. So this is what an inflection point looks like. So what we're going to do now is sketch what the graph of f dash of x would look like. So because fx is stationary at points A, B, and C, its gradient, or its first derivative, would be 0 at each of these points. So the graph of f dash x, it would hit the x-axis at A, B, and C. I'm just drawing a rough sketch here. So let's look at the behavior of fx. So before point A, the graph is leaning to the right. It has a positive gradient. It's increasing. As x is increasing, y is increasing before A. So the gradient would be positive. That means that the first derivative would be positive. So what would happen is the graph of f dash x would start up here and it would come down to A. Now after A, the gradient is negative because it's leaning to the left. The y value is decreasing. So because the gradient is negative, the first derivative is negative, it's going to be below the axis for this time, and then it'll turn around and go to B. We don't really care about what this intercept is or where the turning point of the first derivative is. That's not important at the moment. So then after it hits point B, it is positive gradient up to C, so it's going to be above the axis, but then it hits C, the gradient is 0 again, and then it's positive thereafter. So the first derivative is going to go back and hit C. At point C, the gradient is 0, so the first derivative is 0, and then it's positive again after this point. See, it's positive gradient, stationary, and then positive again. So it'll turn around and go like this. So this would be the graph of f dash x. So we're going to use this graph here to look at the behavior of the second derivative. So let's look at point A, which we know was a maximum. So what's happening to the first derivative at point A is it's decreasing. So the first derivative decreasing, how do we write that mathematically? Well, if the first derivative is decreasing, then its derivative, f double dash x, is negative. On the other hand, at point B, which was a smiley face, which was a minimum, you can see the first derivative is increasing. The gradient here in green is positive. So that means, so the gradient of the first derivative is the second derivative. That means the second derivative is positive. So what happened at C, which was the inflection point? Well, what you can see is that here is like a turning point of the first derivative. So that means the first derivative is actually 0 at this point. And this is precisely what the second derivative test is. When you have a stationary point, if the second derivative is negative, then the point is a maximum. If the second derivative is positive, the point is a minimum. And if the second derivative is equal to 0, that's where we have possible inflection points. So that is the second derivative test. I've basically just explained visually why that is the case. If you don't understand why, make sure you remember all of this. So we're now going to use that and test the stationary points of a given function. So we're going to find and classify the stationary points of this function here. Make sure you do both. Find means you have to give the coordinates of the stationary point, and classify, we have to determine whether it's a maximum, minimum, or inflection point. A lot of people forget to do this second part, but I know you won't do that because you're a superstar. So the stationary points, the definition hasn't changed since last year. The stationary points always occur when the first derivative is equal to 0. So if I want to find the stationary points of this function, my first step is to differentiate. So I get 4x cubed minus 18x squared. So now I want to find where that is equal to 0. So for an equation like this, you could use your graphics calculator, because I don't want you to have to do any like polynomial long division. But in this particular question, it's really easy. We shouldn't need a graphics calculator. We just take out the highest common factor is 2x squared. So that will be leaving 2x minus 9. So either the first thing is equal to 0, so that would mean x is equal to 0, or the second thing is equal to 0, in which case x is 4.5. So we need a stationary point. So a point needs an x value and a y value. So when x equals 0, to find the corresponding y value, you just substitute it in here. So if x is equal to 0, f of 0 is just 0. If x is 4.5, f of 4.5 is about minus 136.69. So, of course, that comes from just substituting x equals 4.5 into this equation up here. So we found that the two stationary points are 0, 0 is 1, and 4.5 minus 136.69 is another. Now we're going to classify them. So to classify them, I'm going to use the second derivative test. So I'm going to calculate the second derivative. So second derivative is just the derivative of this one here. So it will be 12x squared minus 36x. So here's now how I use the second derivative test. I substitute in each of these values and see what the second derivative is at that point. So if I substitute 0 into the second derivative, I get 0. Now, if I substitute 4.5 into the second derivative, I don't care really what the number is. I just know it's positive. So as we established on the previous slide, because the second derivative at 0 is 0, what I've actually found is 0, 0 is an inflection point. And because the second derivative is positive at this stationary point, it means it's a minimum. So 4.5 minus 136.69 is a local minimum point. And that's how we use the second derivative test. So I'm just going to make one more quick point. This second derivative equals 0 when x is 0. It also equals 0 when x is equal to 3. But x equals 3 wasn't one of our stationary points. So it turns out that there are sometimes inflection points that are not stationary points. So I just wanted to mention that in case you come across it. We're not really going to look at those in this course. We're basically just going to look at inflection points that are stationary, but I just wanted to let you know. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.